Welcome to this presentation on the 3GPP TR22.876 version 19.1.0, which focuses on the study of AIML model transfer phase 2 for release 19. This study focuses on the application and optimization of AIML within the 5G system, specifically looking at the transfer of AIML models between different entities in the network. I'd like to point out quickly here how phase 1 is different from phase 2 and what are the usual various phases of these kinds of studies. Phase 1 study usually focuses on initial exploration, use cases, basic requirements, and gap analysis. Phase 1 outcomes include feasibility confirmation and initial recommendations. Phase 2 study, just like the document here, focuses on advanced exploration, detailed use cases, enhanced requirements, comprehensive gap analysis, proposed solutions, and performance indicators, KPIs. And the outcomes for phase 2 usually include advanced recommendations and detailed technical solutions. As of my knowledge, the cutoff date for this topic was back in October of 2021. There is no official documentation or announcement of phase 3 or phase 4 studies on AIML model transfer within the 3GPP framework. However, based on the progression from phase 1 to phase 2, potential future phases could be forthcoming. Over the next 21 slides, we will delve into various aspects of this study, exploring its relevance to modern AIML applications and the enhancements it brings to the 5G ecosystem. This 3GPP specification encompasses a rich tapestry of key topics and concepts. I've distilled its essence into a concise yet hopefully comprehensive presentation featuring 11 curated agenda items. These are explored across 23 crafted slides, which incorporated the majority of the specification's original diagrams. Let me go through the agenda items here quickly. First is scope and objectives. AIML operations overview, proximity-based work task offloading, local AIML model split on factory robots, AIML model transfer management, 5G system assisted transfer learning, direct device connection assisted federated learning, asynchronous federated learning, distributed joint interface for 3D object detection, consolidated potential requirements and KPIs. Lastly is the conclusion and recommendations slide. Let's begin. The scope of this technical report is to study the use cases and identify the functional and performance requirements necessary for efficient AIML operations using direct device connections. So this is key, using direct device connections. We'll explore further on this concept here. Our study focuses on three main areas: distributed AI inference, distributed decentralized model training, and conducting a gap analysis of the existing 5G system mechanisms to identify areas needing enhancement. The ultimate goal is to ensure that the 5G system can support these AIML operations effectively, enabling applications such as autonomous driving, robot remote control, and video recognition. In the initial phase, we identified three primary types of AIML operations. splitting operations between AIML endpoints, distributing and sharing AIML models and data over the 5G system, and utilizing distributed or federated learning. Phase 2 of this study further explores how direct device connections can enhance each of these operations, providing more efficient and effective AIML processes. By leveraging direct device connections, we aim to improve the communication capacity and coverage, leading to better task offloading and more efficient AIML training and inference. Okay, first big topic here is proximity-based work task offloading. What is it? As the name implies, it's about offloading work from one device to another. Proximity-based work task offloading allows a device with low computation capacity to offload tasks to a nearby device, leveraging direct device connections. This approach helps manage computation loads and improve performance without necessarily increasing data rates. The conditions for this use case include the device using an AI model like AlexNet. This is an example here. AlexNet for image recognition and having predefined alternative splitting points. During the service flow, the task offloading process involves the device discovering a nearby device, establishing a direct connection with this nearby device, and transferring intermediate data. This ensures reduced computation load on the original device while maintaining QoS parameters. Existing features support direct network connection modes, but we need new requirements for proximity-based work task offloading to complete, and then implementation comes afterwards. We don't have a lot of requirements or all the requirements as of yet, but I'm sure people are working on it or have worked on it, but made their solution proprietary. Okay, let's take a look at this diagram showing the AlexNet model for image recognition. This diagram, I'm going to go look at this diagram in depth a little bit. So stay with me. This diagram illustrates the layer level computation and communication resource evaluation for an AlexNet model used in image recognition. You can see the mobile device on the left, the little icon there, the mobile device, that's the device performing the initial computation for image recognition using the AlexNet model. Look to the right side, you can see the network server. The server that take over part of the computational tasks from the mobile device to reduce the computation load on the mobile device. Then take a look at the candidate split points. There are four of them on the top of the histogram. These are specific points in the neural network where the computation can be split between the mobile device and the network server. Now look at the y-axis on the left, which indicates the layer latency. The latency associated with computing each layer of the AlexNet model on the mobile device. The y-axis on the right indicates the size of output data. The size of the output data or of the data outputted by each layer, which needs to be transmitted if the computation is offloaded to the network server. Now the x-axis on the bottom, layers, the x-axis, that is representing the different layers in the AlexNet model, including convolutional layers, conv in short, pooling layers, pool in short, and fully connected layers, FC in short. You can see those acronyms written sideways near the bottom there on the histogram. And then the final layer called the softmax layer. So the x-axis, again, includes all of these layers. Now, the split points. The candidate, let's take a look at the split point 0, starting from the left to the right. This represents the initial input to the neural network, point 0. There is no latency at this point as no computation has been performed yet. The size of the input data is relatively small. Next, the candidate split point 1, after pool 1 layer. This is after the first pooling layer. The layers up to this point, conf1 and pool1, show significant latency, indicating substantial computational effort. The size of the input data from pool 1 is larger compared to the input, reflecting the intermediate data generated after initial layers of processing. Candidate split point 2, after pool 2 layer. This is the second pooling layer. This is after the second pooling layer. The cumulative latency up to this point includes the latency from conf2 and pool 2, which is still substantial, but less than the first split point. The data size here is smaller than at split point 1, indicating some reduction due to pooling operations. Candidate split point 3 after pool 5 layer. This is after the fifth pooling layer. The cumulative latency up to pool 5 is lower than the previous split points, reflecting reduced computational demand as the network progresses. The data size is significantly reduced, making it more feasible to transmit intermediate data if offloading is necessary. Now the final split point, the split point 4, the candidate split point 4, final output. This is at the network's final output stage. The cumulative latency includes all previous layers and the fully connected layers. The size of the final output data is minimal, as it represents the condensed classification result. So for computational load management, we need to select appropriate split points. That is, the computational load on the mobile device can be managed effectively so that the computational load can be managed effectively on the mobile device. For example, if the device has low computation capacity or battery, for example, your mobile phone is low in battery, earlier split points can be chosen to offload more computation to the network server. The size of the output data at each split point influences the data transmission requirements. Later split points result in smaller data sizes, reducing the transmission load on the network. We need to also consider latency. There's latency considerations. The latency associated with each layer impacts the decision on where to split the computation. Lower latency layers can be processed on the mobile device, while high latency layers can be offloaded to reduce the overall processing time. Okay, that's all I'd like to say for this diagram. I think it should be quite self-evident what it is trying to convey. Moving on to the next diagram, this is also about AlexNet, the AlexNet model, looking at it from a slightly different angle. Not a histogram now. This is really sort of a flow, how things flow. This diagram illustrates two scenarios related to task offloading for AIML inference using, again, an AlexNet model, also for image recognition. The two scenarios are, if you look at the bottom there, one scenario is called no task offloading. As the name implies, the mobile device UEA in this instance, performs all computations up to a certain layer and sends intermediate data to the application server. Look at the top there. Application server is on the top of this picture. Sending intermediate data to the application server for further processing. The B scenario here, task offloading by UEB. It is describing the mobile device UEA offloads part of the computation to a nearby device, in this case UEB, using a direct device connection, synonymous to side link. You heard of the word side link a lot. Side link is essentially a device-to-device, direct device connection, which then completes the computation and sends intermediate data to the application server. In scenario A, no task offloading, the mobile device, which is UEA, performs the computations for layers 1 to 15 of the AlexNet model. After processing layers 1 to 15, UEA generates intermediate data, which is 0.02 megabytes per frame. It's written very small on the picture, but I think you may be able to see it. It's still pretty clear. 0.02 megabytes per frame on scenario A. I'm still talking about scenario A. The intermediate data is transmitted to the application server via the NGRAN, which is Next Generation Radio Access Network, using the UU interface. UU interface, I'm sure all of you know what that interface is, knowing about 5G architecture. The required uplink data rate for transmitting this intermediate data is 4.8 megabits per second, which is much lower than scenario B, you'll see. The application server then performs the computations for the remaining layers 14 to 24 to complete the AI inference task. So that's scenario A. What about scenario B? Scenario B is a task offloading by UEB. So in scenario B, UEA performs the computations for the initial layers 1 to 4 of the AlexNet model. Due to resource constraints, for example, low battery, UEA offloads the computation of layers 5 to 15 to a nearby device, UEB. The offloading is done using a side link, which is, again, direct device connection between UEA and UEB. UEB receives the intermediate data from UEA. In this case, it will be 0.27 megabytes per frame, and performs the computations for layers 5 to 15. After completing its computations, UEB transmits the intermediate data to the application server via the NGRAN using the UU interface. The required uplink data rate for transmitting this intermediate data from UEB is 65 megabits per second. The application server then performs the computations for the remaining layers 16 to 24 to complete the AI inference task. So I want to point out UEA handles a significant computational load in scenario A, which can be taxing on its resources, especially if the device has limited computational power or battery life, like your smartphone. In scenario B, the computational load on UEA is reduced by offloading part of the computation to UEB, enabling UEA to conserve its resources. The amount of intermediate data generated and the required uplink data rate differ significantly between the two scenarios. In scenario A, the data size is smaller, 0.02 megabytes per frame, resulting in a lower uplink data rate, 4.8 megabits per second. Scenario B, as we already stated, the data size is larger, 0.27 megabytes per frame versus 0.02 megabytes per frame in scenario A. Due to offloading, resulting in a higher uplink data rate, which is 65 megabits per second, versus scenario is 4.8 megabits per second. So you can see the significant differences here between the size of the frame per frame and the uplink data rate. Scenario B demonstrates the utilization of side link communication, which is the direct device communications to offload tasks between devices, which can optimize network usage and reduce the load on the NGRAN, the radio access network itself. This approach leverages so-called proximity-based computation, enhancing the overall efficiency of the AIML inference process. We have to think about the quality of service. Task offloading requires careful management of QoS parameters to ensure that the end-to-end latency and data rates are maintained at acceptable levels. In scenario B, the QoS parameters on both the side link and the UU interface need to be adjusted to accommodate the increased data rate and ensure seamless task offloading and data transmission. In both of these scenarios, the application server finalizes the AIML inference by processing the remaining layers of the AlexNet model. The server must handle the intermediate data efficiently, regardless of whether it comes directly from UEA or from UEB after task offloading. It doesn't really care. It still have to handle the intermediate data efficiently. All right, that's about all we need to talk about. Next slide is about another use case, which is using the same concept. In a modern factory setting, autonomous robots assist human operators by performing tasks and ensuring safety. When a robot's battery is low, part of its AIML model can be offloaded to another robot or a service hosting environment. This slide covers the detailed description, service flows, and pre- and post-conditions of this use case. For the service flows, that's exactly like what we talked about in the previous slide, how the data being transferred, the intermediate data, and how the flow works. So this is sort of a narrative repeating some of the things we already said. So we also, on this slide, we have pre and post conditions of this use case. The preconditions include multiple robots sharing AIML models and sensors, while the service flows involve offloading tasks to maintain efficiency. Post conditions ensure continuous operation despite low battery levels, and existing features like proximity service support these operations. There's no comprehensive requirements written up yet on how to enhance data transfer capabilities for efficient AIML model splitting. And even if it exists, it's not on this spec. It will be on a separate specification. Next is AIML model transfer management. AIML model transfer management involves using direct device connections to relay or store AIML models, ensuring stable and reliable model transfers. The preconditions include the MEC storing various AIML models. The MEC, is an acronym for Multi-Access Edge Computing or Mobile Edge Computing. They're the same. MEC, Mobile Multi-Access Edge Computing, storing various AIML models and high-quality plans for volunteer UEs. The service flows detail the model transfer process, including QoS acceleration and network exposure for volunteer UEs. Post conditions ensure continuous AR services, augmented reality services, and improved model transfer processes. Existing features support position-related data availability and relay UE selection. Again, there are no comprehensive requirements written up on this yet, but I'm sure that there are already implementations based on some proprietary requirements based on use cases. There's a picture to further illustrate what AIML model management through direct device connection, how it works. It's pretty simple, actually. Let's take a look. This diagram illustrates the AIML model transfer management process through direct device connections. And it's, I think, section 6 on the spec, if you want to refer back for more information. It demonstrates how AIML models are managed and distributed among UEs with the assistance of volunteer UEs, operator services, and third-party control. So those are the elements or components of the diagram. So let's take a look at the blue arrows first. The blue arrows indicate model transfer path. These are path, the arrows indicates the path through which the AIML models are transferred between devices. The green dashed lines represents the control mechanism for managing the transfer of AIML models. So those are model transfer controls, green dashed lines. Those orange double-sided arrows represents volunteer UE selection, showing the process of selecting volunteer UEs to assist in the model transfer. So what does each of these elements do? For the operator MAC, multi-access edge computing, operator MAC, it is responsible for storing various AIML models and facilitating their transfer to UEs, which I already said this earlier. It also interacts with the operator's 5GC, which is 5G core, and the third party to manage the distribution and control of AIML models. The 5G core network plays a crucial role in coordinating the MAC, volunteer UEs, and regular UEs. It's like a coordinator function in the 5G core network, in the 5G core element in the 5G network. It ensures the models are transferred efficiently and securely. For this third party, the third party, for example, could be a service provider or application developer, sets the policies and requirements for the AIML model transfer. So their function is to set policies and requirements. It also communicates with the operator's MAC and 5G core to manage and control the transfer process. Volunteer UEs are devices that are well connected to the base station and are selected to assist in relaying AIML models to other UEs. These devices, these volunteer UEs, act as intermediaries to ensure stable and reliable mobile transfers, especially when direct communication with the base station is challenging for some UEs. UEs are actually the end devices that require AIML models for various applications such as AR headsets, augmented reality headsets, autonomous vehicles, or smartphones. They receive the AIML models either directly from the MAC or through volunteer UEs. The third party, as we said earlier, sets the policies and requirements for model transfers and then communicate them to the operator's 5G core and MAC. The 5G core and MAC work together to manage the control mechanism of the model transfers. The operator's 5G core, based on the policies set by the third party, selects volunteer UEs that are well connected to the network. These volunteer UEs are chosen to help relay the AIML models to other UEs, ensuring efficient and reliable distribution. So I think I covered all the elements here and what exactly this is showing us. Okay, that's all I wanted to describe on this picture. The next is assisted transfer learning. Transfer learning leverages knowledge from pre-trained models to improve training efficiency and accuracy. By using direct device connections, privacy concerns can be mitigated as the model is transferred directly between user devices. Preconditions include intelligent driving services and agreements for AIML model sharing. The service flows cover the model transfer process and fine-tuning based on local data. Post-conditions ensure efficient model acquisition and enhanced intelligent driving services. Existing features support indirect network connections and exposing information to third parties. Again, we need some requirements or newer requirements to be established so that we can have effective transfer learning in 5G systems. So here's a picture that follows this topic, the model transfer learning. What it is illustrating here is the concept of 5G system, assisted transfer learning for trajectory prediction between two user equipments, two UEs. Specifically here, it is clearly stated UE1 and UE2. The process depicted involves transferring a pre-trained AIML model from UE1 to UE2, where it is then fine-tuned based on local data from UE2. This method leverages the 5G network to facilitate the model transfer efficiently. The device that initially uses and holds the pre-trained AI model is UE1. The device that receives the AIML model from UE1 and fine-tunes it based on its local data is UE2. The 5G network supports and facilitates the model transfer processes between UE1 and UE2. It's pretty clearly stated here. So UE1 has an AIML model that has been pre-trained and used for a specific task, such as, again, trajectory prediction in intelligent driving. That's one use case of many use cases. Its functionality is using this model, which has been pre-trained on data that is relevant to the environment and use cases specific to UE1. Then this model in UE1 is transferred from UE1 to UE2 through the 5G network. The transfer allows UE2 to leverage the pre-trained model from UE1, which can significantly reduce the training time and computational resources needed for UE2 to achieve a similar level of performance. The beauty of this is, and I said this already, the UE2, after the model is transferred to UE2, it can then adjust the model based on its local data, based on the local data that reflects the environment that is unique to UE2. So this fine-tuning based on local data is very beneficial after the model transfer. What does the fine-tuning does? It simply involves adjusting the model parameters to better fit the specific environment and use cases of UE2, and the outcome would be that the fine-tuned model being optimized for the conditions and requirements of UE2, providing or improving its performance and accuracy. So this is a simple enough diagram. Next is assisted federated learning. Federated learning, which is a slightly different concept, still is rather simple, as the name implies. You do learning collaboratively with direct device connections, and this allows devices to share training results locally, not training model now. This is sharing training results locally, improving model accuracy and reducing reliance on a central server. Preconditions include an application server for federated learning and transmission delay requirements. The service flows detail the decentralized average method, where local model updates and are aggregated globally. Postconditions ensure continuous model training and optimized federated learning performance. We'll have a picture follow this to explain further. Existing features support monitoring network resource utilization and predicting network condition changes. Again, we need good written requirements if we want to enhance federated learning through direct device connections. That is yet to be worked on, and people are publishing what their specific requirements are based on use cases. So here is the diagram that will explain further the concept of federated learning, FL in short, with a decentralized average method, specifically using the lazy metropolis algorithm. Lazy metropolis algorithm, if you want to look at the details, Google it. As I always say, all the information is at your fingertips. If you want to learn more about any of these, you can just look up in the from the internet. So this lazy metropolis algorithm is one of the two methods. The diagram indeed here compares the performance of the original FL, original federated learning, with the federated learning using this lazy metropolis method in terms of identification accuracy over the number of learning steps or learning iterations. The decentralized averaging method aims to enhance the performance of federated learning by reducing communication overhead and enabling more devices to participate in the learning process. So here we have on the diagram device A and device B. These devices participate in the FL process. I'm going to say FL process, meaning federated learning process. Okay, so device A and device B participate in the FL process using the lazy metropolis algorithm. The communication paths represent, and we have two of them here, these communication paths represent the data transmission between devices and the central server, which is the original FL, and then between devices themselves, which is using the lazy metropolis FL. Those are the two. The distances between devices are indicated, showing the range of communication. So we are looking at a performance graph. This is a performance graph, essentially. Y-axis represents identification accuracy, the accuracy of the model in identifying or classifying data. X-axis represents the number of steps or iterations in the learning process. The red dashed line indicates the original FL, the performance of the traditional FL method. The black solid line represents the performance of the federated learning method using the lazy metropolis algorithm. We are comparing the two, the original and the FL using the lazy metropolis metropolis algorithm, and that is represented by the black solid line. So take a look at the two communication paths, right? The original FL is green in color on the top, near the top there. So in the original FL, devices transmit their local model updates directly to the central server. The central server aggregates these updates and sends back the global model. This method relies heavily on the central server and requires all devices to communicate with it, which can lead to high communication overhead and delays, as you can imagine, especially for devices with poor connectivity. The other path, purple in color, you can see the FL with lazy metropolis is the purple path. The purple path indicates devices communicate with each other to share their local model updates. The lazy metropolis algorithm is used to aggregate these updates in a decentralized manner. This method reduces the reliance on the central server, or getting rid of it altogether. It does not go to the central server, and allows devices to update their models more efficiently by sharing updates with nearby devices. The communication paths and distances between devices show the decentralized nature of this approach, enabling more flexibility and reducing the communication burden on the central server. There are the two different lines, as we talked earlier, the red dashed line and the black solid line. The red dashed line, which indicates the identification accuracy of the original FL method, as you can see, it increases steadily with the number of learning steps, but it plateaus at around 0.85, right? You can see it's not that small. It plateaus around 0.85. The performance is limited by the communication overhead and the need for all devices to synchronize with the central server. That's pretty taxing. Now the black solid line, that's FL with lazy metropolis. The identification accuracy of the FL with lazy metropolis method increases more rapidly and reaches high accuracy levels, plateauing at around 0.89. The difference is not that crazy, but if you look at the inset graph, it highlights the difference in performance between the two methods, showing that the lazy metropolis method consistently outperforms the original FL method in terms of identification accuracy. And we know the reason why, right? We just talked about the reason why, because of the overhead. This improvement is due to the decentralized averaging method, which allows for more efficient communication and aggregation of model updates, enabling more devices to participate in the learning process. So there are many use cases. Image recognition is one use case that is being used throughout this specification, but you can think of all the others. I'm not going into more use cases. If you want more for reference, you can look up the spec. But the concept is exactly the same using what we just described. That's the idea of assisted federated learning. Moving on, this is even a simpler diagram, but we'll take a quick look at it. This diagram illustrates a scenario where two UEs, Bob and Alice, perform decentralized federated learning, FL, using direct device communication, bypassing the central application server. You can see the two big red crosses here indicating the communication between Alex and Bob are between each other and not bother to go up to the application server. This approach is particularly useful when the UEs have poor network connectivity to the central server, but can communicate directly with each other, with other devices. So that's what it is. I'm not going to talk more because we already know what the application server does and what the two UEs are doing, how they transfer AIML models. Okay, so it's a very simple picture. Next, let's talk about asynchronous federated learning versus synchronous. This is asynchronous federated learning. ASYNC-FL, as is the acronym. It enables UEs to report results when ready. When it's good and ready, it will just report the results without waiting for all devices to synchronize. This method is more resilient to varying network conditions and device capabilities. Preconditions include the availability of direct and indirect network connections and relaxed communication requirements. The service flows describe the async-FL process where relay UEs determine QoS for member UEs. So there's a new entity here. Relay UEs doing something, determining QoS for member UEs. So we'll take a look at a picture later to further understand. Post conditions ensure efficient model training and proper charging for indirect communication. Existing features support aggregated QoS, quality of service, and exposing information to third parties. Again, we need new requirements to be established for this if we want to fully support ASYNC-FL via direct device connections. Here's the picture. Another simple picture, if you look at it carefully, it illustrates the concept of ASYNC-FL within a group-based setup. It shows how member UEs can perform federated learning with the help of a relay UE. Look at in the middle of this picture, there's a relay UE pointing to UE1, which acts as the relay UE. So this picture shows how member UEs can perform federated learning with the help of a relay UE, especially in scenarios where some UEs are in areas with bad network coverage. The diagram highlights the communication flow between the parameter server, relay UE, and member UEs. The parameter server is the central entity responsible for aggregating the model updates from member UEs and distributing the global model back to them. The relay UE is a special UE, UE1 here, and it's designated to assist other UEs that have poor network connectivity. It acts as an intermediary to relay data between the parameter server and other UEs. The UEs participating in the federated learning process are called the member UEs. Some UEs are in areas with good coverage, while others are in areas with bad coverage. The Async-FL concept really is just about communications between member UEs. It represents the asynchronous federated learning process where UEs share updates with the parameter server and other UEs without waiting for synchronized updates. You can imagine it's much more efficient this way. The role of the parameter server collects model updates from the member UEs and aggregates them to update the global model. It then distributes the updated global model back to the member UEs or through the relay UEs to the other UEs. The server communicates directly with UEs that have good network coverage and indirectly with those in bad coverage through the relay UE. So it's pretty clear. Hope you follow. I don't know if I had jumped a diagram. But we can take a look at this. This is a diagram illustrating the concept of joint inference among multiple vehicles for 3D object detection, enabling enhanced situational awareness and safety in autonomous driving scenarios. The vehicles collaborate to share and process data, leading to a more accurate and comprehensive object detection. So the idea is very simple. We have vehicle 1 here, a vehicle equipped with AI and sensors for object detection. We have third-party vehicle, which is another vehicle involved in the joint inference process. We have these other vehicles, which are simply additional vehicles contributing to the 3D object detection task. So how does this object detection come about? Each vehicle performs local object detection using its own sensors and AI capabilities. Detected objects are shared with other vehicles to enhance the overall detection accuracy. When we say joint inference, the idea is that we have a collaborative process here going on where vehicles share their detected objects and inference results with each other. This leads to a more comprehensive understanding of the environment as information from multiple perspectives is combined. So the idea is pretty simple. Here's another picture that illustrates the concept of distributed joint learning of 3D object detection, emphasizing how combining local maps from multiple vehicles leads to better inference performance. The collaborative approach here helps to create a more accurate and comprehensive global map, improving the detection and understanding of objects in the environment. So it's a little bit messy here. What we're looking at is that there are 3 local maps: local map 1, local map 2, and local map 3. These are maps generated by individual vehicles using their own sensors and AI algorithms. Each local map represents the vehicle's perception of the environment based on its own data, own sensor data. The global map, on the other hand, is an aggregated map created by combining the local maps from multiple vehicles. It represents a more accurate and comprehensive view of the environment. So what is the ground truth, quote unquote? The ground truth refers to the actual positions and dimensions of objects in the environment. The ground truth is used as a reference to evaluate the accuracy of the local and global maps. So for local map 1, which is blue in color, the text local map 1 is written in blue. That is created by one vehicle using its onboard sensors, for example, cameras, LiDAR, radar, etc. It represents the vehicle's perception, which may have inaccuracies due to limited perspective or sensor noise. Local map 2, green color, it's written in text, and the map is like a rectangle, is also in green. This is generated by another vehicle with a different perspective and sensor data. It adds additional details and corrections to the overall perception. And then you can see there's the local map 3, written in yellow color. This is contributed by a third vehicle, further enriching the collective understanding of the environment. The global map, as you can see, the global map went through the aggregation process. Local maps from multiple vehicles are combined to form the global map. The aggregation process involves aligning the local maps and integrating their data to correct inaccuracies and fill in gaps. So here the global map is red in color. The resultant global map provides a more accurate and comprehensive representation of the environment. By incorporating multiple perspectives, it reduces the uncertainty and errors present in individual local maps. And we can use the ground truth as reference data. The ground truth, as we said, it represents the actual positions, dimensions, and orientations of objects in the environment. It can serve as a benchmark to evaluate the accuracy of local and global maps. The diagram shows the alignment of the local maps and the global map with the ground truth. That's why you can see these overlapping rectangles one over and over the other. It's comparing these different maps with the ground truth. The global map in red closely aligns with the ground truth. So that goes to show global map is much more accurate. That indicates improved accuracy over the individual local maps. So that's all initially what this picture is trying to convey. And a specific use case example would be autonomous driving in an urban environment. You need all the information you need for your environment for autonomous driving to be safe, to be working as it is intended to be. So that would be a common use case. Okay, another use case here other than detecting 3D objects, is to detect whether there are accidents around. So this is again a joint inference, so same thing, joint collaboration between each other. The devices collaborate to get more accurate information. Joint inference among multiple vehicles for accident vehicle detection. So this is just another use case. Same concept. This illustrates the concept again for joint inference among multiple vehicles for accident detection. Again, many things are the same. It demonstrates how vehicles equipped with AI and sensors of their own collaborate to detect and identify an accident vehicle on the road, enhancing situational awareness and safety. We have the accident vehicle. This vehicle involved in an accident positioned in the middle of the road here on the picture. And then this vehicle is surrounded by debris and potentially hazardous objects. So the other so-called participating vehicles, like Alice's vehicle, which is an autonomous vehicle approaching the accident scene. There are other vehicles, multiple vehicles equipped also with AI and sensors contributing to the joint inference process. Each vehicle is equipped with AI systems and various sensors, again, like cameras, LiDAR, radar, to detect objects and gather data about the environment. So just like the previous example, the collaborative process where vehicles share their sensor data and inference results is to improve the detection and identification of the accident vehicle. It involves communication between vehicles, allowing them to aggregate and refine their observations. All right, this is the second to the last slide. This slide consolidates the potential requirements and KPIs, key performance indicators, identified across the various use cases. For authorization, the 5G system must support user consent and operator policy to authorize specific UEs for data transmission. QoS, Quality of Service Control, involves configuring and modifying communication QoS and monitoring QoS characteristics. Information exposure includes exposing relevant information to third parties and assisting in UE member selection. Charging mechanisms must support direct device connections for AIML applications. These consolidated requirements form the baseline for subsequent normative work. In conclusion, this study has identified several use cases for leveraging direct device connections in AIML operations, including split operations, model transfer, and federated learning. We've gone through several different variations of these three topics and how each of them work. The findings highlight the potential for significant improvements in performance and efficiency. We recommend proceeding with normative work based on the consolidated requirements identified in this report, establishing a baseline for future developments in AIML model transfer using direct device connections. These advancements will enhance the efficiency and performance of AIML applications within the 5G ecosystem, paving the way for more robust and effective solutions. That's the end of this presentation. I hope to see you in the next 3GPP presentation. Goodbye.